of the course. Like this is like a third order topic. Like, you guys have questions about the material, feel free to ask. All right, well, let's see here. I have an idea for a problem. Yep.
Is there any way to represent n-dimensional spherical Jacobians?
Like what's the...
Because I noticed that 2 dimensions, it's just the radius.
Mm-hmm.
In 3 dimensions, it's the radius squared times
Sine phi. Right.
In 4 dimensions, it's radius cubed sine phi, sine squared
Psi, yeah.
So is there any way to generally represent that using some sort of formula?
Yeah, like that pattern continues is true. I'm hesitant to write down like the general formula. I'd have to introduce a bunch of notation to do it, but well, I think our time is better spent on something else today. But yes, it is possible. And if we could write down that that pattern, maybe we could figure out the formula for the volume of an n-sphere, right? That is something we could try to do. But I think it would take me more than 15 minutes, though. So, how about this? Imagine you have a volume which is bounded man, I keep getting bad markers today. A volume which is bounded between, let us say, E bounded by x equals to, well, not x, I want y. Y equals to x squared plus z squared minus 4, and y equals to 6 minus x squared minus z squared. Calculate, the integral over e of, I don't know, square root of x squared plus z squared dv. So what are these surfaces that we're looking at? Do you guys recognize what you're up against here? These are paraboloids, right? But they're paraboloids in what sense? First of all, let's make sure my question makes sense, right? So I think that one looks something like this. It's y is equal to minus 4 over here, right? So it's like that. And that one is, I don't really know what, I think they're going to meet on a circle. And here's like 6. So this one would be y is equal to x squared plus z squared minus 4. This one I think would be y is equal to 6 minus x squared minus z squared. But they have their zenith on the y-axis, right? Where x and z is both 0, we've got our minimum or maximum values for those paraboloids, and I think they meet in a circle, right? I think they meet in a circle there. And so the question makes sense, I think. Yeah? What's this intersection circle? Where does that happen? we just need to do what? X squared plus z squared minus 4 equals to 6 minus x squared minus z squared, right? So apparently 2 times x squared plus z squared is equal to 10. So x squared plus z squared is equal to 5. So basically this right here, I'll call it s, is the square root of 5. So like, I think this is a problem that suggests defining, modified cylindrical coordinates, right? I'm going to say, let's see here. I'm going to say x is equal to s times the cosine of beta. I'm going to say z is equal to s times the sine of beta. And I'm going to say y, well, y is y. So let's use these modified cylindrical coordinates to do this problem. Yeah? So with these modified cylindrical coordinates, I can see that apparently, like basically I could think about cutting all space. First of all, I cut into a giant tube, right? 0 less than or equal to s less than or equal to the square root of 5. Right? That fits me inside here. And then if I cut out this, I've got, what's my bounds for y? I've got x squared plus z squared is s squared, right? So I've got s squared minus 4 less than or equal to y less than or equal to 6 minus s squared. So that's what being, between the left and the right defining surfaces for y in terms of my modified cylindrical coordinates is just that. And then the beta, well, beta's free. There's no restriction on beta whatsoever. So I'll do that one last, 0 to 2 pi. And my s is ranging from 0 to the square root of 5. My y ranges from s squared minus 4 all the way up to 6 minus s squared. All right. So what's the deal with the this right here is what? Yeah, that's just s, right? And this is going to work out to s dz, ds, d beta, right? Oh, yes, thank you. Oh, yeah, duh. Okay, so I've got s squared dy ds d beta. So the beta, just let's get the beta done with. That's a 2 pi, right? And then we've got the integral from 0 to the square root of 5. Oh, that's unpleasant, isn't it? Oh, no, it's not, because with the y integrations first. So I've got s squared times 6 minus s squared, parentheses are our friend, minus s squared minus 4. And then I still got my ds integral to do, right?
Are we just integrating this dy? Because it's square root. Or no, wait, so when we put it on this.
Okay, yes. You almost talked me out of it there for a second. So we got 2 pi integral from 0 to the square root of 5. We get a 10 s squared, right? And minus 2s to the 4th. All right. And so I get 2 pi 10 square root of 5 to the 3rd power divided by 3 minus 2 times the square root of 5 to the 5th power divided by 5. Which is 2 pi times 50 over 3 minus (50 over 5) times the square root of 5, which is, okay, 2 pi times 100 over 15 square root of 5. So if I haven't made a stupid arithmetic mistake, (40 pi square root of 5 divided by 3 maybe? I don't know. But anyway, I wanted to give you an example like this where we actually had the problem of, oh, we kind of understand the shape, but our standard cylindrical coordinate system doesn't work for us, right? So we have to shift the coordinate system. So there is, this is kind of like the second order problems that we haven't done a lot of. But the next thing that you'd actually like to be able to do is, if your shape is like, here's a less fanciful version of this, is like, you might have an integration where you've got you're integrating over a sphere, right? But the sphere is not centered at the origin. Do you know what to do to fix the spherical coordinates, to shift them somewhere else, right? Like if I'm calculating, for example, the integral over x minus 1 squared plus y minus 2 squared plus z minus 3 squared less than or equal to 25 of, the square root of x minus 1 squared plus y minus 2 squared dv. Do you know what to do? What you'd want to do is build a new spherical coordinate system where you've got, x is equal to 1 plus rho cosine theta sine phi. Y is equal to 2 plus rho sine theta sine phi. Z is equal to 3 plus rho cosine phi. If you'll allow me to abuse the notation rho and theta and phi. Like, you don't have to invent new letters for your non-standard coordinate system as long as you tell me what you're doing, all right? So anyway, that's it for today. I will not release the math battle early. I want you guys to sleep. So just come to class fresh tomorrow.